Welcome back. In the previous section, we learned that finding the probability of an event turned out to really be a counting problem. We had to count how many ways there were for the event to occur and count how many things there are in the sample space. So now we're going to take that idea and apply to it what we've previously learned about counting. So we're going to be looking at experiments where we're going to need to think about combinations, permutations, factorials, the multiplication principle, inclusion, exclusion, all of those sorts of things are going to come back here. So let's get started with some examples. For this first example, we've got 6 numbered red balls. When I say numbered, you can imagine them having like a 1, 2, 3, 4, 5, 6 written on them. And same thing with the green balls. They have numbers written on them, which means I'll be able to tell them apart. So I can tell selecting green ball number 1 versus green ball number 3. I'll be able to tell these green balls from themselves. They're all distinguishable. First things first, we are making a selection of 3 balls for this experiment, and we're selecting it without replacement. So when I say without replacement, I couldn't select red ball number 1, red ball number 1, and red ball number 1 for a third time, because every time I select a ball, I'm taking it out of the urn and I'm not able to select it a second time or a third time. So when I'm saying selecting without replacement, that means each ball can be selected at most once. That also means if we're thinking about what's happening for this experiment in general, so when we're thinking about counting our sample space, we just have to think about how many ways are there for us to do this experiment, no restrictions. So for this experiment, if you're just selecting 3 balls, no restrictions, and you wanted to know how many ways there are to do that, well, we have 6 red and 5 green. There's 11 balls in total, and we're making a selection of 3 of them. So we are going to just do a combination, 11C3. That should be the number of things inside of our sample space. And I know it's a combination because I'm not interested in the sequence in which I picked these balls out. So it doesn't matter to me if I selected red ball 1, red ball 2, red ball 3, or I selected red ball 3, red ball 2, and red ball 1. That's still the same thing to me. I don't care about the order in which I selected them. I'm just making a selection. So combination it is. And now for the experiment that we're interested in selecting 3 balls, and now the event is the event that exactly 2 balls are green. So we'll have 2 green balls as our event. And for that, I'm going to have to think about the number of ways to count that event. And for that, to select 2 green balls, there's actually really 2 tasks. There's selecting 2 green balls and also selecting 1 red, because we have to select 3 things in total. So there's 5 green balls, so 5C2 should be the number of ways for me to select 2 out of the 5 green balls. And there's 6 red balls, so 6C1, that should be the number of ways for me to select a red ball from the urn. And so then the probability that I select 2 green balls should just be the number of ways to select 2 green balls, which is 5C2 times 6C1, divided by the number of ways to do the experiment, which is 11C3. And that gives me a probability of about 0.3636. Okay, now what if I decided I wanted to select all 3 balls to have the same color? So if we're thinking about this, first off, the experiment hasn't changed, so our sample space has not changed. It's still 11C3. That's kind of the good news here. Once we know what our sample space is, it'll be the same for all the other parts. The only thing that's changed is the event, and the event is that all 3 balls are the same color. And if they're all the same color, that's really 2 options. It's either they're all red or they're all green. So really I've got 2 things to count. I need to find the number of ways to get all green, and I need to find the number of ways to get all red, and I need to add the 2 things together. That's our inclusion-exclusion principle. If we're selecting all green marbles, then there's only one thing to do there, which is out of the 5 green marbles, I'm going to select 3 of them, so 5C3. And if I'm going to select the all red marbles, then again, there's only one thing to do, which is out of all the red marbles, select 3 of them. And so now, probability of us getting all the same color should be the number of ways to get all the same color, which is 5C3 plus 6C3, divided by my sample space, which is 11C3. And that gives me a probability of about 0.1818. Now there is another technique that I want to throw into the mix here, which is similar to counting with the complement. So if we're remembering from before when we were counting, if you were looking for the number of ways for something to happen, the number of things inside of an event, a set A, you would just count up the universe and then remove the things that you don't want. This is kind of a similar idea here, except we need to remember that it's not the entire universe that we're subtracting things from. It's the probability for that entire universe. In other words, we take the probability for that entire sample space and we remove the probability of the thing that we don't want to get the probability that we do want. The idea basically comes from a Venn diagram. If you're thinking about a sample space and having some sort of an event E in there, if you wanted to know what was the probability of E, you could say, well, I know the probability for the entire sample space is 1, so I'll take 1 for the entire sample space and then subtract the things that are outside of E. So take the probability for the sample space and subtract the probability of E complement. And then what should be left over should be the things that are inside of E. I should be left with the probability of E itself. So in the same sort of way when we were counting, how I would stop and say, we really need to think about, is this easier to count using the complement? The same thing will be true for probability. I'll have to ask myself, is this event easy enough to count directly, or would it be easier to count the complement? Okay, let's do an example. We're back to our marbles again, the numbered marbles. We're selecting 5 of them this time. So we've changed our experiment. So in this case now it's a selection of 5 marbles. So the sample size, instead of being 11C3, our sample size is now 11C5. Okay. Now, we're interested in what's the probability of at least one of them being red. And if I'm thinking about getting at least one being red, there are 5 different scenarios, because you could have 1 is red, or 2 is red, or 3 is red, or 4 is red, or 5 is red. So if I wanted to do this directly using inclusion-exclusion, I would have 5 different probabilities to compute. I'd have to find the probability of getting 1 red, or 2, or 3, or 4, or 5, and then add everybody up together. I'm thinking about the opposite, though. What about the opposite of at least one marble being red, or at least one ball being red? And the opposite of one or more things being red would be that nothing is red. So in other words, using the complement, it would be a lot faster. I would just do 1 minus the probability of my event not happening, 1 minus the probability of me getting 0 red marbles. And that's easy to do, because to get nothing red, that means everything would have to be green. And to get all green marbles, that's easy enough to do with just counting. We know that there are 5 green marbles, or 5 green balls. So there are 5C5 ways to select 5 green balls out of the 11C5 different ways there are to select 5 marbles in total. So now we just need to compute for ourselves 1 minus 5C5 over 11C5. And that gives me a probability of about 0.9978, thereabouts. So if I were to select 5 of these 11 balls at random, the probability of me getting something red, at least one of them being red, is pretty good, 0.9978.